So just a minute, I'll have to reopen this. Yeah. So let us look at the operation of another gate. So first of all, what is the first thing that we would like to check? So what we said last time is that uh, your circuit can basically be split around the output. Okay, this is the output. Let me just redraw this. So it can be split around this output line. So you have, a dual. So what you have is a series parallel dual. Okay, so let us see. You have A and B in series over here. In series, you have A and B in parallel over here. Rather, you have got these two transistors in parallel over here. You have got these two in series. You have got these two in parallel, and further you have got these two blocks in parallel. Over here you have got these two blocks in series. Okay, so you can see that you do have a series parallel dual over here. All right, so what you can do is we can just leave this as it is, and let us just open another instance. And let us see how it works. So as usual, we'll follow the same method that we followed yesterday. So what you find is that if A and B are if both A and B are 1, you have a parallel path. This is for A, or let me just say that again, well, for A equal to 1 and B equal to 1. All right. So if A and B are high, you would expect the output to go low, right? And you got to check that if A and B are high, you don't have a path from VDD to this place. That's why you have the series parallel dual. So you can see that if A and B are high, this is, you can say, cutoff. If A equal to 1 and B equal to 1. So that justifies this part. that justifies this part. And you can see that this is symmetric, so it is quite evident that in a similar way this will also be satisfied. So this gate, so as you can see that this is also a gate. So can you, well, if you write down the truth table, you'll have 16 entries. So can you just write down the truth table? By the way, this, as you can see, this is called an AND or invert. That is for AND or invert gate. All right. So I hope anyone has a question regarding the operation of the AND or invert gate. Are you all okay with it? All right. So let us look at the next one. So this is, as you can see, it's an OR and invert gate. Okay. This is an OR and invert gate. This is AND or invert. This is OR and invert. All right. It is quite evident that it is OR and invert. All right. So I think I don't really need to explain the operation of this gate separately. You can quite easily follow the operation. So is that okay? Are you comfortable with the operation of the OR and invert gate? Yeah. Yeah, there are some questions here. If you have a question, it is better you speak up, because it is difficult for me to, check that you are okay. So, all right. So let me just see. What are your questions? Yeah, if you have a question, please speak up. So, okay. So first question that I had is, which one do you know? So I think, do you see any difference? First of all the, so again, let us draw that. These are P. So do you see any visual difference between the way these transistors are drawn, the P-type transistors and the N-type transistors? Do you see any visual difference?
Yes, sir. There is a black dot.
The black dot.
Just a minute. Probably my yeah. Can someone speak up? I'm not sure whether.
Hello.
Hello.
Yes, sir. Sir, can you hear me?
I don't. I don't know. Something seems to be wrong. Anyway, I'm not getting any sound. I don't know whether you're speaking or not, but at the moment I'm not getting any sound. Uh, Hello, can someone speak up? Oh, okay. All
Yes, sir,
right.
we are
All right. I think for the time being, I'll have to, because very soon Professor Mitra will be taking up, so I'll just finish it. Okay. Yeah, I think I should have tested it before starting the lecture. Okay, so you can see that there is a visual difference that the PMOS transistors are represented with a black dot at the gate. Okay, I mean this is not the only way to represent a PMOS transistor, but this is one of the conventions. All right, this is one of the conventions. You can follow this convention. All right. Yeah, so Kaushiki wants the slides. So we'll be putting up the slides. Once we finish with a set of slides, we'll put those up. You'll have all the slides. We'll just put those up after we finish with a set of slides. All right. Any other questions, or maybe you can type now. I seem to have a problem with the mic. So, do you have any other questions? You can type. All right. Okay, so let us just go over to the next circuit. Yeah, so this is another gate. Of course, I've written the function of the XOR gate. I think, why don't you just try to check that it's indeed an XOR gate. So, so how will you check that it's an XOR gate? Okay, so let me tell you how you can check a little more easily. So if you have noticed earlier, all of these, the gates that you studied earlier, all of these had a complementation, right? So XOR, you can say, is the complement of XNOR, okay? So you can say that uh, if you just look at it, this is, you can say, equivalent to the complementation of XNOR. uh, I'm not sure whether there is a separate, so I'm just writing it this way. It's a complementation of, or maybe I'll just write it a, all right. So it's a, so if you just consider how XNOR works, then you can just treat it as a complement. So that's why, if you remember, I had so this is, you can say, if where that's the XNOR function. I mean, you'll just find it easier to, you know, explain the working that way. The two are the same actually. Yeah. So why don't you? So why don't you just you know do it as you had done last time? Why don't you write down that operation table and post it? Just just form the operation table, and why don't you just post it here? So that will be a good exercise. Yeah. Just do that quickly. In the meantime, maybe I'll try to rejoin. Yeah. Okay, so have you done it? Has anyone uh, has anyone I don't remember the circuit. Okay. So the circuit is actually uh, rather why don't you yeah, so why don't you try to figure out what the circuit will be? That will be a good exercise actually. Let us say X naught. So what should be the circuit? So you have a notion. So you can draw the truth table. You can draw the truth table of XOR X naught and try to figure out under what conditions you should under what conditions the function will be low. All right, and accordingly you can draw those the corresponding structures in the NMOS side, and once you have done that, then you just draw the complementary structure on the PMOS side. So that will actually give you the circuit for, let us say, the XOR gate. So yeah, in fact that will be a more relevant exercise because you know how to draw the operation table given the circuit. So why don't you try to do it the other way around? That is, when you know the function of the gate, how can you get the structure? How can you form the structure of the gate using this transistor? So yeah, rather yeah, why don't you just try to draw that circuit?
Sir,
The
it's the XNOR gate, right?
it's an XOR gate, but as I told you, if you remember what we have been doing all this time, what we have been doing all this time. So if you look at this, here we have been writing it as a function.
CRM, can you share it once again? Can you share your
Yeah,
slides once again?
I'm showing another gate. I'm just showing another gate.
Okay, okay.
Yeah, so if you look at this, see, this is this part.
So we can't see anything.
Oh, it is not. Oh, sorry, it is not shared. Sorry, I'll just do that. Right, I'll just do that. Oh. Oh, 1 second. Can you see now? I hope you can see now.
Yes.
Okay. So yeah. So just see. Uh, what you said is that your function is so if you look at this, um, if you look at this is the this is the function. This is uh, 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 what it said is that this is the AND or invert gate. All right. So it realizes the invert of the AND OR function. All right. It's so here your function is FAB. Okay, here it is FABCD. It is AB or CD. Alright, so you're realizing what you're realizing is F bar. Alright, so here what is the function? The function, as you can see, is just is A or C and B or D, and you are realizing F bar. So when you are so so now just think of the function. Let f be a x naught b. So what you will be realizing is f bar, that is a x or b. All right. So, so the circuit structure, as you can see, this one is so this basically it goes low. That's why it is complement. So when A and B are high, you have a conducting path to the ground. When C and D are high, you have another conducting path to the ground. All right. And otherwise, if that is not the case, then you don't have a conducting path to the ground. So that is why it is the complement of that, right? So what you have to do is, you want to get Ax or B. So you consider the complement of that function. So whenever that function is true, that is whenever Ax not B is true, you want to have a conducting path to the ground, right? That is what you are doing really. So that is how you can build the gate. So do you understand it? Hello?
Yes, sir, you audible.
Yes, sir.
Yeah, where is that? Uh, yeah, so can you use that principle now to to get the structure of the XOR gate? So you consider the truth table of XNOR, all right? Identify the situation when that is XNOR is true, and under those conditions you provide a conducting path to the ground, and then once you have done that, just the series parallel dual of the NMOS network will be your PMOS network. All right. So just try to use that principle to draw the circuit structure of the XOR gate. And you can post it in your notebook.
Sir, excuse me, sir.
Yeah.
Sir, I'm not able to figure out how to come up with the function without writing the truth table or just by looking at the figure.
All right. Let us see. Let us try to do it. Let us try to do it. So, okay. So we want. So you want to realize. What do you want to realize? You want to realize the XOR. You want to realize A XOR B. Okay. This is what you want to realize. So we are going to we want F A B as the complement of A XOR B. All right, that is the XNOR. All right. So what is the truth table of that? A B and A XNOR B. All right. So let us get the truth table of that. So when is X not true? X naught is true when both A and B have the same value, right? That's when X NOR is true. Alright? When both of them have the same value, and otherwise they're false. Alright. So what do we want when it is true? What do we want? Can someone tell me? Hello? What do we want when X NOR is
We want VDD to be connected to the output.
Yeah, no, wrong. We want a conducting part to the ground, right?
When it's 1, right?
When X NOR is true, because we are going to realize F
Okay,
bar.
sorry.
We are going to realize F bar. Alright. So how can you have a conducting part to the ground? Let us see. So if this is your transistor, you can have a conducting part to the ground as follows. This is your NMOS transistor. A, B. So if A is high and B is high, you have a conducting part to the ground. Is that all right? Is that okay?
Yes, sir.
Now let us see. But that's not the only case. You also want a conducting path when both A and B are low, right? So let us try to do that again. So here I'm going to put A bar. Here I'm going to put B bar. So just check. So when A and B are high, I'm going to have a conducting part to the ground. When both A and B are low, then also I'll have a conducting part to the ground. So I can check this and I can check this. Is that okay?
So instead of putting A bar, can't we put a PMOS and A?
No. Just see what we are doing. We want a conducting part to the ground. All right. So when you want a conducting, because how does the PMOS work? When the gate is high, you have a conducting path from the source and the drain, right? So when A is high, you want this to conduct. When B is high, you want this to conduct. So that's why you're using NMOS transistors here. Now what I told you is that you're going to have dual. You're going to have a dual structure over there. So let us see what are the. So you have, let us say, you have a structure here. You have one structure here, and you have got another structure here. These are in parallel, right? These are, sorry, let's just, you got one structure here and you got another structure here. So these two structures are in parallel. So you want to have, in the dual part, you want to have these two, you want to have the dual of these two in series. So let us try to do that. So you want these to be in series. So you have VDD there. So I'm just drawing a cloud over there. Okay, I'm drawing a cloud over there and another cloud over here. So these two are going to be the dual structures of this, and these two are going to be in series, right? These two are in parallel, so their duals will be in series. Now what is the dual of this? These two are in series, so I want to have these in parallel, right? So I'm going to have these in parallel, but over here I'm going to use only PMOS. So and I have a similar structure over here. So this is AB, okay? So I'm going to put AB here. And this is A bar, B bar. So I'm going to put A bar, B bar here. Alright. And this is my output line. So now check whether, so this should give you the complement of this. So whenever, so it should give you the complement of x naught. It should give you the complement of x naught, right? So this is it, you want it to, it should be f bar, where f bar is the x naught function. So the complement of the x naught function should be the XOR function. All right. So this is, f bar complement is going to be should be the XOR. So now check whether this is actually the XOR function. Can you just check this yourself now? You have got the circuit, so can you check it yourself? Just try checking it. Yeah? Can you check it?
Sir, I have one question.
Yeah. Yeah.
Sir, why are we drawing the upper part as the dual of the lower part?
Okay. Why you are doing it? Because whenever the lower part is conducting, the upper part should not be conducting. And whenever the lower part is not conducting, the upper part should be conducting, right? That is why you are drawing it as the dual.
Okay, sir.
So are you able to satisfy yourself that the circuit that has been drawn uh, does indeed uh, compute the XOR of A and B?
Yes, sir.
It works. So now you understand the principle, right? It is a fairly simple principle, but you just got to do it that way. All right.
I
So
have a question.
yeah.
So, like, in for drawing this circuit, we needed A bar and B bar. So, but A bar and B bar are not really present. So, like,
So why not? I mean, see, it's not so difficult. I mean, if A bar and B bar are not present, then you can always use an inverter to get A bar and B bar, can't you?
yes, sir.
That's what we did last time. So, you can draw it this way, for example. So you have A and you have A bar. It's not so difficult.
Okay,
All
sir.
right?
So that's a simplification we are making. Like, we are assuming we are doing the inversion elsewhere.
Sorry?
So that is a simplification we are making, that we are doing the inversion elsewhere, but we are not showing it to keep this thing clean and
Oh yeah,
neat.
yeah. So we are showing the inverted signal. So you have to get the inverted signal somehow. There are certain gates which uh, produce both at once, but anyway, that's all right. Yeah. So you're assuming that you have the inverted signal somehow. Yeah. All right. So I hope this is all right with everyone. Anyone else have a question? All right.
Sir,
Then let
can
us
we
just.
make the
Sorry.
circuit in some other manner?
Just come once again. I couldn't hear you.
Sir, can we make the circuit in some other way? Like, hello?
How you? Yeah, this is how you realize the CMOS circuit. This is how you realize the CMOS circuit. Uh, minimizations apply to this circuit construction. I mean, that should be evident to you, right? If you can, if you can minimize the expression, I have written a certain expression for this function. So if you can minimize the expression, so you can just construct a structure for the minimized function as well. So minimization, it is possible to minimize these networks when that is applicable. Yeah. But what is, I mean, was that your question, or did you have something else in mind?
Yes, sir. Like I was thinking that we can draw the upper part as a parallel combination of A B bar and A bar B. So I thought that will also work.
No, see, uh, the upper part, if you are talking about the XOR function, it should be in this form. It should be in this form. Uh, uh, because if you, I mean, it should satisfy this requirement. So here, what you can see is that if I mean, it has to be the dual of this for the reasons that I explained. So whenever you know your complementary function, that helps. I mean, the complementary function helps us to realize the lower part. I mean, you can always start with either the lower part first or the upper part first. That is up to you. For me, I just find it a bit convenient to start with the NMOS network first. So if you are constructing the NMOS network, basically whenever the complement is 1, you need to have a path to the ground. And once you have covered that, just dual of that will give you the PMOS network. Okay. All right. So yeah. So let us just so that is the XOR gate. So yeah, that is the XOR gate. And let us look at another kind of gate, which is called the transmission gate. This is called a transmission gate. So look at the structure. So here you have two terminals, just as you have two terminals of a switch. So if S is high, just see what happens if S is high. So when S is high, this PMOS transistor, the gate is at a high voltage, and if you look at the lower one is an NMOS transistor. So for the NMOS transistor, the gate is at a high voltage, and for the PMOS transistor, the gate is at a low voltage because that is S bar. Okay, so just know that. So when S is 1, so when S is 1, uh, let us say this is high. So let us just say S. This is called this P, call this N. All right. So let us just draw the. So when S is high, let us consider the gate of. So when S is high, so let us call this the gate of PMOS. So the gate is high, right?
Both are closed.
Yeah, and this is low. All right. So what happens is, uh, if
So
if
it should be opposite.
have I done it wrong? Let me. Yes. So that is true. So let me just correct it. Yeah. So when S is high, yeah, that's right. So when S is high, this is low and this is high. Okay. So now this is high. Now suppose A is at a low voltage. Okay. Suppose A is at a low voltage. So uh, so you have, let us consider two possibilities here. Let us draw a separate line in between. And so let us consider A. So A is, let us say, we consider two possibilities, low and high. Okay, when A is low and when A is high. So if A is at a low voltage, so again I'll draw P and N. Alright, so when A is at a low voltage, then you know that this is closed, right? Because the gate is at a high voltage, A is at a low voltage, so you have a potential difference here which will populate electrons in the gate. Alright, so that's when, sorry, again I've made a mistake. That is when the N-type transistor will be closed, right? So when this is high and this is low, for this combination the N-type is closed. On the other hand, if A is high, then you have PG low and this is, so in that case this is closed. Alright, so what about these? Okay, first of all, I hope these two are clear, right? So if A is high, and your this gate of this PMOS is low, then you have seen that there is the situation when this channel conducts, right? So that is when this will be closed. What happens in this case? When A is low and when A is high, when A is, let us say, when A is high and N is high. So when A is high and N is high, you do not have a significant potential difference. So this is, I'll say, you call it weak. So in this case, the channel formation is weak. But so let me just put that in a different color. So let us say in that case the channel formation is weak. But in this case, the channel formation is strong. So that's why you have two transistors. All right. So in this case, when you have two transistors, at least one of them will be closed. All right. So as you can see that NMOS transistor is good for transmitting low voltage, whereas a PMOS transistor is good for transmitting a high voltage. All right, and you look at the other situation, that is when S is
Sir, you are muted.
yeah. So when S is low, of course, then you have the gate of this is just the opposite. This is low and this is high. Okay, and again you consider those two cases. This is low and this is high. So now you just see. So you can see that. So when A is low, okay, when A is low, that time if your this is high, when A is low, and if this is high, then there is no benefit really. So you find that and similarly, if this is basically when the gate of a PMOS transistor is high and when the gate of a NMOS transistor is low, so it is basically off in all cases. All right, off in all cases. So you can say that in this situation, you can say that you can say that in this situation it is transmitting, and in this situation it is off. So that's why it is called a transmission gate. It's called a CMOS transmission gate. All right, or I'll just write it that way. It is called a CMOS transmission gate. So that is how this CMOS transmission gate works. All right. So let us just go on, and this is the symbol for the CMOS trans. Yeah.
So can
Yes.
you explain the weak channel thing again for the S high case?
Sorry.
So can you please explain the case where S is high and that weak channel is formed for P?
See, weak channel is just that this is of no interest, really. So these are the cases of interest. These are the cases of interest. These are the cases of interest. Okay. And weak channels are basically means here the channel is weak. So it doesn't matter. I mean, even if it is off, it doesn't matter. But it is not off; it is weak. So this one doesn't play any useful to these transistors. Is it okay? Hello.
So your voice was breaking. So can you please repeat?
Yeah. So these circled cases. These are the. So this is when the transistor is closed. So here the N-type transistor is closed, and in this case the P-type transistor is closed. So these are the cases which these are the cases for which the gate is transmitting. Okay, these are the cases for which the gate is which leads to the transmission of the gate. So as you can see, it is covering both the cases, low and both cases, A low and A high. Both cases are covered. All right. So these are the cases when the gate is transmitting, and these cases, like these are kind of irrelevant because you have one transistor which is transmitting. This is parallel with that. This transistor, as you can see, it is in parallel with that. So it transmits weakly. So it's okay. I mean, it doesn't create a problem. All right.
Yes, sir.
All right, but in this case, what is important is in this case, in all cases, there is no transmission. So when S is low, this gate is off. It is like the switch turned off. In this case, the switch is turned on. It is transmitting, so you can say on. All right. So And this is the symbol for the CMOS transmission gate. This is the symbol that you use for the CMOS transmission gate. All right. And now you can again, look at the circuit that I've drawn on the right. Can you tell me what it does? It is now easy to, I mean, it should be quite easy for you to explain what it does. So I'll just keep this also here. If you, yeah. So can you tell me what
Either transmit A or B.
uh, yeah. So can you just put it a little better? So when does it transmit A? When does it transmit B?
When S is 1, it will transmit A, and when S is 0, it will transmit B.
Yeah, that is right. So this is what is called a multiplexer. So you can write down the output in this form. So here you can write the output in this form. So it transmits A when S is high, right? So you can say SA or S bar B. Is that okay? Yes? You can write X in this form, right? And this is also called a 2-to-1 multiplexer. Alright, this is called a 2-to-1 multiplexer. So that is the way a multiplexer works. Is that okay? Alright, so that is the end of this lecture. Okay, alright, that's all for today.